in computer algebra, especially as applied to special functions and orthogonal polynomials. He wrote a great book way back that competed with A plus B and in some ways did a much better job. Wolfram is also a great graphic designer. He just gave me a present. This beautiful, delightful computer-generated candy, sucking candy with this 3D plot. And he gave me an idea for my annual Valentine's Day project. So, Wolfram will talk about computer algebra methods for orthogonal polynomials. As usual, we're going to take the speaker, in this case Wolfram, for dinner, 6:45 Evelyn. If you'd like to join us, everybody's welcome, but let me know after the talk ends. Thank you.
Yeah, thank you very much, Doron, for this invitation, for the organizers to invite me to this colloquium. And I will speak about this topic here. And to go into details, I use computer algebra here. In this talk, I will only use one system, namely Maple, with which you probably are used with, but you will see it is easy to use. We will use some algorithms, just as black boxes from the computer algebra, namely mainly algorithms from linear algebra, but here many variables are involved if we do deal with special functions. Polynomial factorization is a very important issue, and here again the multivariate case occurs. And finally, we will see that sometimes we will need to solve nonlinear systems of polynomial equations, and we do that also as a black box. Of course, internally, something like resultants or Groeper bases will be used for that purpose. So now let's go into the topic. If you don't know something about orthogonal polynomials, that's not very important, because you know something about orthogonality from linear algebra. And related to orthogonality, there is always a scalar product. And now assume if you have an infinite dimensional vector space and the space of functions, continuous or something, then you can define such a scalar product. There is an integral from alpha to beta, f times g, and then the mu of x, where here mu is either considered as a Borel measure supported in this interval, or equivalently as a Riemann-Stieltjes integral with non-decreasing function mu. So this is what you can think of, and actually we will do it much easier now. In this talk I will speak only about this case, namely we assume that this d mu is an absolute continuous measure. Then in this case the d mu can be written as rho of x times dx, and rho is just a positive function that will occur and will be called weight function. A second case, which will also be considered at the boundary, will be the discrete case. Here mu is a discrete measure, and in this case this integral finally collapses to a sum, either finite or infinite. Okay, now we will ask polynomials to be orthogonal. Actually, we will only consider the following case. A set of polynomial is given, it's an infinite sequence, Pn, such that the degree of the nth polynomial Pn is exactly n. So this is what we assume. And therefore, you can write Pn of x is kn times x to the n plus kn prime times x to the n minus 1, etc. Kn is the highest coefficient and always is assumed to be non-negative, to be non-zero. Then such a system of polynomials is called orthogonal, as usual, with respect to a positive definite measure, if the scalar product of Pm and Pn is equal to 0 for m not equal to n, and is positive in the other case. So that's the positive definiteness of the measure that we are interested in. So this is the setting in which we will look at. Now, from the definition we get some results. First result, every orthogonal polynomial sequence, OPS, satisfies such a relation. X times Pn can be written as a linear combination of the three highest terms appearing here. So first of all, this is the proof. X times Pn is a polynomial of degree n plus 1, for sure. Therefore, it can be written as a linear combination of all the previous polynomials, because it's very easy to show that orthogonal polynomials must be linearly independent. Therefore, you can write down such a thing. Then apply the integral, and you will see by orthogonality that all these terms down there by Pn minus 2, etc., must be 0. Very simple. And therefore, this is a major result, which is really very clear and easy to derive. So, these 3-term recurrences are valid, and it has a lot of consequences. One consequence, the zeros of orthogonal polynomials are simple, so there is no zero which has order 2 or such. Lie in the interior of this interval that we have considered, alpha beta, where the support is given, and have some nice interlacing properties. I cannot go into the detail because of time restrictions, but that means, for example, Pn and Pn plus 1, Pn has n zeros, Pn plus 1 has n plus 1 zeros, and they interlace with each other. And the third thing, which is always valid in the orthogonal setting, you can define these guys here, the moments, so you can enter x to the n in the definition of this integral with the mu there, and you will get some numbers mu n. And if you plug in these numbers mu n and then the monomials down there, then you will get the Pn of x. Besides a constant, actually these orthogonal polynomials are clearly uniquely determined besides such constants, so these constants cannot be determined by the process. So this is what we get in general. Now we switch towards a much more limited range, namely towards the so-called classical continuous families. Now we start from scratch, we restart. But keep in mind what we have said about orthogonality before. So now we start with a differential equation. Assume we want to have an orthogonal polynomial system, OPS, which is a solution of this equation. For the moment, sigma, tau are completely arbitrary functions. Lambda is only depending on n. So that's what we assume. Completely arbitrary. But now, since Pn must be exactly a polynomial of degree n, we can look at this in more detail. We look at n equal 1. What happens? If n is equal to 1, then this is a polynomial of degree 1, this is a constant, and this is 0. Therefore, you can conclude tau must be a polynomial of degree 1. Very easy. So we write tau is d times x plus e, d and e are some numbers. Now, look at n equal 2. What happens now? If n is equal to 2, this is a polynomial of degree 2. This is a linear polynomial. This is another linear, this is again quadratic. And Pn double prime is a constant. And therefore, sigma must be a polynomial of degree 2. No other choice. And we write always sigma a times x squared plus b times x plus c. So now we know sigma and tau are not arbitrary. This is what we have. And then we can even compute lambda n, because if we look now for the highest coefficient, which is exactly the nth coefficient, then we see we can compute lambda n is this number. We will do this computation later with Maple again. So this is what you have. This is a very simple thing. So you have a quite simple structure. And therefore, already in 1929, this was considered by Bochner, and he gave a complete description of the picture, what we get, based on this differential equation. Namely, assume we plug in sigma, everything depends on sigma. Assume we plug in sigma equals 0. Actually, that's a very special case, because then the differential equation is not second, but first order. In this case, there are solutions of this type, namely the powers x to the n. Are these orthogonal? Who can prove that these are not orthogonal? Never ever for none of these possible mu's.
It's of the complex.
We gave some corollaries about the zeros. Think of the zeros. We said,
No multiple zeros.
Yeah, this is a multiple zero. So never ever, this is not orthogonal. This cannot happen. But all
But
these
in the real world, in the complex world.
yeah, we'll only consider the real case here. Okay, now assume sigma is a constant, not zero. Then we will get the Hermite polynomials. Everything is modular linear transformations, so we can put the constant equal to 1, and also we can put a 0 exactly at the origin. Then we get the Laguerre polynomials. If we have two zeros, namely we put them at the points 1 and -1, we get the Jacobi polynomials. Actually, Jacobi is a big class containing Legendre, Chebyshev 1, 4, 2, 3, 4, whatsoever, and Gegenbauer. So this is a big, huge class. And then there is a final thing. Assume it has 1 0 only. Sigma has a 1 0, but at a double zero. Then we get the Bessel polynomials. Actually, these in the regular case are not orthogonal on the real line, but in some instances they are, so therefore they are contained in this list. So this is a complete description of the picture, only these cases can occur. What was necessary for the whole computations that we do to do this, and we will see how it goes in the next slide. First of all, we need a very nice family of functions. In our case, these were the powers. The powers appeared here, and that was exactly the family that we need. We will also see that we can write all these as power series. So exactly these powers are very important in the classical case. And it was necessary to have an operator. This was the differential operator in this case, with a very nice property that if you apply the differential operator to this x to the n, what you get is again a member of this family, namely n times fn minus 1. So these two properties are exactly the reason why so many things work so fine, and we will remember that later for the other cases. Here are the four people, Hermite, Laguerre, Jacobi, and Bessel, who gave the names to these polynomials. So this is now the reason why these polynomials stemming from a differential equation, and therefore this was not clearly why they should be orthogonal. Why they are orthogonal, if you take this differential equation, multiply by the function rho, which is a solution of this very simple first order differential equation, then using some partial integrations, you can see that two polynomials with not equal n, so with n and m, have a scalar product with respect to this measure rho here, which is 0. This is not difficult, it's half a page. Writing, you need some partial integrations, but that's it. So you can say, if this Pearson differential equation is satisfied for a certain function rho, sigma is our polynomial of degree 2 and tau our polynomial of degree 1, then we have orthogonality with respect to this rho. And of course, this is an easy exercise to solve this differential equation, so you can write down the rho explicitly. So if sigma and tau are given, rho is determined, and we are done. A constant, of course, has to be determined such that this is a positive function, otherwise it will not work. So this is the whole structure that we have here. Now I give you a list of, I think 6 or 7 different definitions that we could use to define the same families. We started with the differential equation. That was my favorite. If we start with the differential equation, it turns out you get exactly these families. But we could also have started with the Pearson differential equation. So we could have searched for such a rho, a weight function, which satisfies this equation. Then one can show the polynomials that we find there are orthogonal and satisfy this differential equation. So we can also start here with the Pearson. Also, another option is, assume you have a family Pn, which is an orthogonal polynomial family, and you wish that the derivatives are also orthogonal. If you do so, then you get only the families we have seen already. That's another definition. Or, here's a derivative rule. This is a very nice thing from the point of view also of computer algebra. I use this very often. So we have this function sigma again. Sigma times Pn prime is a polynomial of degree n plus 1 at most. And therefore, again, we can write down such a linear combination of all these polynomials. And again, now by orthogonality and by the use of the differential equation, it's more complicated. We can see that all these coefficients that come later disappear. And if we start with this here, we get again the same family of polynomials. Or else, we use this structure relation. The name structure relation already tells you this is a structure which comes up exactly here. Here in this relation, our polynomials themselves are written in terms of their derivatives, and the main thing is that all these are constants here. No x appears here on the right-hand side, nothing like this. And if you have such a relation, you get exactly the same families that we saw before. Or finally, the Rodriguez formula. The Rodriguez formula is a formula which gives our Pn in terms of an nth derivative of something. And if you have this structure, you will only find the families that we saw already. So you see, this is a very, very strict thing. These classical orthogonal polynomial systems satisfy so many different things, and you can define them in many different ways if you wish. Okay, now let's switch a little towards another topic. Namely, we started with a differential equation, and we ended up in some certain families for which the absolutely continuous case applied. Now we have another case, namely the discrete case that we looked at, and now we would like to find some families for this. Then you need another operator, of course. You cannot start with a differential equation. The right operator to look at here is the delta operator, the difference operator. Delta f of x is f of x plus 1 minus f of x. Actually, one needs a shift operator as well, but if you have these two, then you can do a rather similar theory and get the so-called classical discrete orthogonal polynomial systems. And they are solutions of certain difference equations. I don't write down this because it's really a very, very similar theory. I just tell you what are the main ingredients now. Namely, we had the need of a family, and we had the need of an operator. The operator is this one, it's clear. The operator is delta. So now, search for a family of polynomials so that the nth polynomial is exactly degree n, so that delta applied to this family gives a family member again. That's not so easy. You cannot use the powers. This will not be valid. Then you will get into trouble and you will find the Stirling numbers on the way. If you don't do that, then you have to use this function. So this is the so-called falling factorial, x times x minus 1 times, etc. You have n factors here. Of course, that's a polynomial of degree n for n. And if you apply delta on that, very simple computations show that delta fn is n times fn minus 1. So again, we have a very, very similar structure to before. And if you use this, you get a similar theory. You get, of course, a Pearson difference equation, etc., etc. You can do all the proofs that we had done before, again, in the same manner. And what you get is the following families of polynomials. They are, of course, all well known and were defined before this structure was found, namely the Charlier, Meixner, Grafchuk, and Hahn polynomials. So now we have already 8 families or 7 families with names, actually 8, that are in our list. More names will come up, but at the moment this is what we have.
I want to make a comment. This is the calculation. It's really Pascal's triangle.
Yes, okay. So that's what we have now. We have these polynomials. And now we come to another fact, namely all these, the continuous and discrete classical families, can be written as hypergeometric series or functions. And if you don't know that, we have to introduce that shortly. So what is a hypergeometric function? So this is the general definition of a hypergeometric function. It's a formal power series. We call it PFQ with a lot of A's. These are called the upper parameters. And a lot of B's down there. These are called the lower parameters. And a variable, which is called Z here. And it's a power series with some coefficients ak. Z's are variables, so therefore it's ak times z to the k. And the summands that occur here have a very simple relation, namely they have a rational term ratio. That means the quotient alpha k plus 1 divided by alpha k is a rational function. And it is completely clear how the rational function looks. It's namely factorized in the numerator, in the denominator. So here the a1 up to ap occur again, that you saw before, they appear here. The b1 up to bq occur there. These are the lower parameters. By some historical reason, there's an extra k plus 1 here. We don't care. And the z is the kind of highest coefficient that appears in the rational function. That's our variable. So if you have this situation, we can give this function a name and call it the generalized hypergeometric function. Doran would say series because it's a formal power series. The people from orthogonal polynomials and special functions consider that a function. So what is the trick here? First of all, this is a very old concept. Already Gauss introduced this function for p equals 2 and q equals 1, and later on many people worked on that.
Euler was the first.
Even Euler, I'm sorry, I have to forget Euler, that's not good. Now what is the trick? The trick is we have a very simple recurrence relation for the coefficients ak, namely a recurrence relation of first order, and this alpha k, the summand is called a hypergeometric term, satisfying such an easy recurrence equation. So I have to distinguish always between a hypergeometric term, which is the summand of such a series, and the hypergeometric function, which is the series itself. Now, since we had factorized this rational function, it's now very simple to even find a formula for the alpha k, for the a k. And here is the formula. It consists only of so-called Polynomial symbols or shifted factorials. These are again shifted factors like the other guys that we saw before, that were the falling factorials. These are the rising factorials. A times a plus 1 up to a plus k minus 1 k factors appear here. So if you see the ratio ak plus 1 divided by ak, you can easily read off these coefficients, and you don't have to do an induction proof anymore. So this is the formula that we always use in our world. So now we go back to the classical systems and look for the Laguerre case and other cases as well. Namely, first of all, assume we start with the differential equation. We have the differential equation. Now we can plug into the differential equation this power series. So if we do that, then f and f prime and f double prime are substituted. And now if we collect like powers and equate coefficients, then we get a recurrence equation for the coefficients. That can be done also with computer algebra. I don't have the time to show it here, but it's very simple. So this is a recurrence equation for the coefficients. And in some cases, this is a very simple one. For example, in the Laguerre case, it turns out this recurrence equation is first order. That means the coefficient of the Laguerre polynomials, considered as a power series, is a hypergeometric term, and we can easily read off the term, and here is the hypergeometric function related to the so-called Laguerre, generalized Laguerre polynomials, ln alpha x. They can be either written as this hypergeometric function 1f1, or else, some people of course like that better. Now it's a sum, it's a normal sum, and you have just a binomial coefficient appearing here. And this is of course the same. If you have the sum and use the formula for the coefficient here, you can easily find out that this function here, because alpha ak plus 1 divided by ak is exactly what you have here, namely, I don't write it down this now, but you can read off these coefficients directly. Now, this is not only the case for the classical continuous, but also in the classical discrete cases, we always get hypergeometric functions. This time, of course, theory is a little different. Here the x appeared in the variable, and here the x appears as a coefficient here. It cannot appear in the variable because otherwise we would have a power series, but the family of powers is not the correct family for this case. But these guys here, they are related to the falling factorials, and therefore this is what we get here. So in the Hahn, in the Grafchuk, in the Meixner, in the Charlier case, we have similar situations like this one. So all these families are well known and have hypergeometric representations and can be dealt with easily. Now, I would now to give my first computer algebra introduction. Namely, I would like to compute something which was computed in 1985 by Leski without computer algebra, of course. He never in his life used computer algebra, but we will do, yeah. Namely, using linear algebra, one can compute the coefficients of the following identities. Especially, we will be interested in the recurrence equation. This was done by Leski. The other identities were done by me and my colleague Schmerzer in 1998. Here's the recurrence. Here are the differential rule. And here is the structure relation. All these three relations have some three items that we have to find. And we find them always the same strategy. We know that these are correct results, and we just have to do what we now do for this case only. The other cases are absolutely similar, and you can do it as an exercise at home, no problem. So we'll do that now with Maple. We will start a Maple session and do the first computation. And you will see at the first place it will take a while, but then it will work fine. So first of all, you will soon see we have a problem. We have problems with many variables now. First of all, we define sigma and tau. Sigma is our generic polynomial ax squared plus bx plus c. Tau is dx plus e. Now we have already 6 variables involved. As it goes on, then p is this polynomial. We only use the 3 highest coefficients because we only need to get 3 informations for alpha and or a n, b n, and c n. And you see there are more variables involved. Now we have already 9 or so, and it goes on. So now we plug in into the differential equation. Okay, this was just the differential equation. We have our p inside. We sort for like powers. Actually, we do a little more. We divide this differential equation. Actually, it's the left-hand side, which should be 0. We divide it by x to the n because we later want to ask for the nth coefficient. Maple is not able to ask for an nth coefficient if n is a symbol, but we can ask for the 4th coefficient very easily. If we divide by x to the n minus 4, the 4th coefficient is the highest that will be asked for. So that's what we have to do, collect these powers. We have many, many items here, and now we look for the highest coefficient, which is the 4th, and solve this equation for lambda n. I told you already what we get is this formula that you saw before. This is exactly the proof for this formula. But now we can go on. What is the next thing? You still, kn prime and kn double prime still occur there. We would like to find them. Here is how we find kn prime. We plug in lambda n, and then we get kn prime is nothing but a rational multiple of kn. And this rational function depends only on a, b, c, d, and e, and n, of course. And if we go one step further, looking for the highest coefficient now, we will find out that kn double prime is again a complicated rational multiple of kn. And we could go on and on. If we would like the 3rd highest, the 4th highest coefficient, we always get such informations. For us, these informations will be the ones we need. Because what we wanted to do is get something for the recurrence equations. For the moment being, we make some things a little lighter. We define kn equal 1. That's the monic case. Then these are the 2 rules to be considered in the future. Now, this is our recurrence equation. We brought everything on the left-hand side. Should be 0 again. Now we can plug in everything we know, namely the pn's. Okay, now the pn's are inside, and now kn prime, kn double prime can be also plugged in because we know they are just multiples of kn. Now everything looks really nasty. We again have to divide by x to the n and a certain power. That's what we do here. You don't want to see the whole term here, really. You don't want. But nevertheless, don't mind. We are only interested in the highest coefficient now, not the rest. And this, of course, is a very simple result.